as 0. Similarly, 1 carry in is propagated as 1 and carry out is propagated and carry in when is propagated here as 1. So this is what we call propagate. So we have 3 different functions: carry kill, carry generate, carry propagate. Kill is also sometimes called delete because it becomes 0, so we call it delete. So it's very easy to see that when carry out generated, say, let us say, denote that by G is when A and B are 1. Carry out is killed, K, when it is A bar into B bar. Now, carry is propagated, P, when A is not equal to B. That means either A or B is 1, which is A exclusive or B. That is A bar, B, or A, B bar. So that is corresponding to this. This is A bar, B, and this one is A, B bar. So we have now identified there is some intrinsic property of the carry out, and we'll use this information to design the circuit. Okay, and that's why the circuit designers have it better insight about these things than the logic designer. Logic designer just bothers about these expressions. So keeping this in mind, let's see what we should do to design a good adder circuitry. So this is basically the same thing what I talked about. The carry gets killed in this case, no matter what the value of input is, output is 0. Carry gets generated here, no matter what the value of input is, output is 1, when A and B are 1, 1, and the other case is carry is propagated. So that being the case, I can now design a 4-bit adder by just concatenating the carries like this. So the carry out of the previous stage goes in as the carry in of the second stage. Carry out of this goes in over here. Carry out of this is going over here. Why am I doing that? Because in primary school, when in primary school they don't teach the binary system, they teach you the decimal system. Say you have 1, 2, 3, 4, you're adding say 9, 8, 7, 6, or rather let's say 5 and 4. So what are we doing? We are adding sequentially from the least significant bit or least significant digit because it's in the decimal system. So we are adding that 9, the carry out is 0, and this 0 we propagate over here. So let's say carry out over here, we propagate over here. Now we are adding this segment. So the first we did the leftmost, then we do the next one, these 3 together, which is 10. So it generates 1, which is put back into the next stage, and then we add this to find out that this will be giving us 7. So out is 0, then we bring it over here, and then finally we add this section as 0, carry out is 1, and then this carry out we write over here. So this is our result. So this process is basically replicated in computer to do the same way. So what we did here is that we generated the carry in or the carry out of this stage and fed to the next stage as the carry in. The carry out of this stage is fed as the carry in of the next stage, and so on. And that's what exactly those things are. So effectively, the carry which is generated at any stage propagates or rather ripples through the different stages, and that's why it is called ripple carry adder, RCA. So this is the simplest form, and very easy to connect them. So the ripple carry adder, despite the fact that it has limitations if you want to do the large additions, because you have to propagate the ripple or rather pass the ripple all the way to the output state, it takes longer time. But still, we do use it, and for your project would show that how you can use the ripple carry adder without losing the performance. So addition part is pretty straightforward. All we need to do is to just hook up the carry out with the carry in of the next stage. What about, so that's the addition. What about subtraction? The good thing about digital or Boolean computing is that we can do all different operations with this block full adder. We can do the subtraction operations, we can do the multiplication, we can do the division, okay? Only thing is that you'll have to do it cleverly. If you want to subtract this function in your primary school, then we need to borrow one here and we write over here, and then we find out that this will be again 5. So there is a notion of borrow in and borrow out in subtraction function the way we learn. Fortunately, the same thing we can do which they don't teach in high school or rather at all in your school. What is called tens complement or nines complement. If they have taught you this, then you would have found out that you are doing exactly the way the computer works. Anybody knows what the nice complement is? You do? Can you go there and do the subtract that? Here. Sure. So what you're doing is that you're subtracting that number with this number, yes? No, I'm not asking that. I'm asking that you need to subtract this number from this number using 9's complement and 10's complement. No, you don't know binary yet. You are in a kindergarten or not? In primary school. Anybody in the class? Any volunteer? You can do it? Okay, you have taken the digital logic from me, so
the name is very suggestive. It's nice compliment, right?
Right.
So just think about it. Something should be add up in order to make them 9.
Okay, you can go back. So basically, you have the positive numbers and negative numbers. So you can write it 1 plus 1 plus 2 plus 3 plus 4 and so on. Now here, depending on the scale, right, we can write it here minus. We can write it minus 1, minus 2, minus 3, minus 4. So in this way, we subtract, and in this way, we add. But the problem is that if you represent in this way, so this is what is known as the sign magnitude. Sign magnitude. Where the magnitude is denoted by these numbers over here, and the sign, this side is negative, that side is positive. If you try to do the sign magnitude subtraction in computer, it becomes very cumbersome in terms of hardware. Our claim is that this simple circuit, where we are just using 4 exclusive OR gates, we can do the subtraction. We don't have to invent a different way to do the subtraction operation. And the same thing will be true for multiplication and division later on. We'll see that, okay? A little different organization, but we'll look into that. So